That means in a normal steady state operation, each control area of a power system should strive to meet its own load demand. That's what I told you, right? Next is that simultaneously your each control area of a power system should participate in regulating the frequency of the system, because you have to regulate the frequency. So therefore, the two basic inter-area regulating responsibilities of each control area are just it's a big one. So I just am explaining what exactly it is. For in system frequency is on schedule, right? Each area is expected automatically to adjust its generation to maintain its net transfer with other areas on schedule, thereby absorbing its own load and own load variation. So long as all areas do so, schedule system frequency as well as net interchange schedule for all areas are maintained. That means suppose you have 4 different power system areas, right? So every area has some contact with other areas such that this much power one can, I mean in general actually buying and selling power, something like this. So each your what you call areas, they have some buying or selling power like this, right? Some area that is your what you call. So in that case, if suppose at a particular time, suppose when I am recording this one, here time is in front of my watch, it is 12:25 p.m. right? At this time, if I have this some power, some contact with everything, and if that same thing is maintained, right, then frequency will also maintain its schedule value, right? So as long as it is maintained, but all of a sudden, if suppose suddenly whatever I had that what you call that schedule power flow and load demand, I know this one. By chance, if it is not, suppose load demand has increased or decreased or something has happened in the system. Of course, system is a stable system, no fault, nothing. You are not considering any abnormal condition. You are considering only normal operating condition, right? So in that case, what can happen that because of this your what you call that different things that load and other things is known. So all the tie line power flow is also known to us, right? But if there is a change, in the load, right, then what will happen? This frequency also will not be on its schedule value, whatever it is given. Same is for this power flow to the tie line, right? So in that case, what will happen? The second one is when system frequency is off schedule, right? I mean it is not because one or more areas are not fulfilling this regulating responsibility. Other areas are expected automatically to shift their respective net transfer schedule proportionally to the system frequency deviation, and in direction to assist the deficient areas and help to restore system frequency. The extent of each area shift to net interchange schedule is programmed by its frequency bias setting. That is, you have little bit we will see later. That is your B. You have seen no D plus 1 upon R frequency response characteristic. That is after we call B. B is the frequency bias setting, right? So detail of this thing cannot be all these things cannot be done in the class. As far as your classroom exercise is concerned, I will see that. But this is your what you call regulating responsibilities of this your what you call basic inter-area regulating responsibility of each control area, right? So this is the idea. So whatever these two things are shown here, that we cannot show you here without your what you call this thing just classroom exercise. But when go for simulation or coding, at that time those things can easily be checked, right, through simulation only. Next is, now I told you many times, the cooperative assistance between areas is one of the planned benefits of interconnected operation, right? Now we will take an example. We will come again that two area modeling and other thing, but first look at this example. A power system has a total load of 1260 megawatt, 1260 megawatt at 50 hertz. The load varies 1.5% for every 1% change in frequency. Find the steady state frequency deviation when a 60 megawatt load is suddenly tripped. If number one, there is no speed control, right? And second thing is, the system has 240 megawatt of spinning reserve evenly spread among 500 megawatt generation capacity with 5% regulation based on this capacity, right? Assume that the effect of governor deadband is such that only 80% of the governors respond to the reduction in system load, right? So total remaining load will be 1260 minus 60, because your here it is given that your there is your what you call 1% find when there is load change suddenly trip, right? There is no there is no this 1260 total load was 1260 megawatt and system was 50 hertz. Load varies 1.5% for every 1% change in frequency, and this is your find the steady state frequency deviation, and 60 megawatt load is suddenly tripped, right? That means your tripped means that load has switched off, right? Something like this. So load is isolated. That means load decrease. First thing is there is no speed your speed control. First one, and second one is the system has 240 megawatt of spinning reserve, evenly spread among 500 megawatt generation capacity with 5% regulation, right? So based on the assume that the effect of governor deadband is such that only 80% of the governor responds to the reduction in system load. Therefore total remaining load is 1260 minus 60, so 1200 megawatt, right? This one. So damping constant of remaining load is D is equal to your 1.5 upon 100 into 1200, because it given the load varies for 1.5% for every 1% change in frequency. So this is 1.5 upon your what you call 100 into 1200 into 100 upon 50 into 1. For simplification, everything I have written for you, right? So basically it will be 1.5 by your 1% of frequency, right? So just written I mean all this thing in detail. So it is under this type of problem we have seen before also. So it is 36 megawatt per hertz, right? So number one, with no speed control means the resulting increase in steady state frequency is delta FSS minus delta PL upon D, because your no speed control means the speed regulation parameter was not there. It was actually something like your if you ask you like your open loop system, something like this. So in that case R term will never come. So it will be minus delta PL upon D. So it will be minus 60 upon 36, because load has decreased to 60 megawatt. That's why this minus sign is taken. That means frequency will increase. So minus 60 upon 36. So that is actually 1.667 hertz. And second thing is the total spinning generation capacity is equal to the load plus reserve. This should be in your mind, right? So total spinning generation capacity is equal to load plus reserve. So 1260 plus 240, that is 1500 megawatt, right? Because it is given no 240 megawatt spinning reserve, your evenly spread among 500 megawatt generation capacity, right? So the total spinning generation capacity is equal to load plus reserve. So load was 1260 plus 240, so 1500 megawatt. So generation contributing to regulation is it is given no your governor is responding to this thing, that your governor deadband is such that deadband will not cover in this, but for numerical sake we have taken this. Only 80% of the governors respond to the reduction in system load, right? So generation contributing to regulation is 0.8 into, because 80% it is, so 0.8 into 1500, so 1200 megawatt, right? Now it is problem in the given a regulation of 5% means that a 5% change in frequency causes your 100% change in power generation. Therefore R is equal to regulation parameter, it is 5% into 50 divided by 1200, right? This is your, because generation contribute to regulation is 1200 megawatt. So in that case R is equal to 0.05 into 50, that is 5% of the frequency. Frequency is 50 hertz divided by 1200 hertz per megawatt. That is actually R will become 1 upon 480 hertz per megawatt. This is actually 480 hertz per megawatt. Therefore 1 upon R is equal to your it is actually 1 upon 480, right, hertz per megawatt. Therefore 1 upon R is equal to 480 megawatt per hertz, just near your reciprocal. Therefore the composite system frequency response characteristic, we know beta is equal to D plus 1 upon R. So D we computed 36 just now. Here it is your this thing, or D value, right? D is 36 megawatt per hertz. Here you have computed, right? And 1 upon R is 480 megawatt per hertz. So 36 plus 480, so 560 megawatt per hertz, right? The composite system frequency response characteristic is, right? Now steady state increase in frequency is delta FSS minus delta upon beta. actually minus delta L upon d plus 1 upon r. So beta we have calculated 516. So minus of minus 16 by 516 hertz. So delta FSS will be 0.1162 hertz, right? So what we have seen, one you see there is no speed control, right? So in that case it was 1.667 hertz, right? When we consider everything, at that time it is 0.1162 hertz, right? So this is another problem. So example 3, a 200 MVA generator operates on full load at frequency of 60 hertz. The load is suddenly reduced to 20 megawatt. Load has decreased. Due to the time lag in governor system, the steam valve begins to close after 0.22 seconds. Determine the change in frequency that occurs in this time, given H is equal to given 10 kilowatt second per kVA. That means H is equal to 10 second actually, because kilowatt and kVA, so it will be dimensionless. Kilowatt upon kVA will not be there. So kilowatt upon kVA means it is a dimensionless quantity. Only second will be remaining. So H actually nothing but 10 second. If it is given like that also doesn't matter. It is 10 second, right, of generating generator capacity. So right. So you have to value the change in frequency that occurs in this time, and these are the data given. So store kinetic energy, 10 into 200 into 1000 kilowatt second, right? It was given that it is 200 MVA generator operates on full load at 60, and load is suddenly reduced to 20 megawatt due to time lag in governor system. So that everything is converted to your what you call kilowatt second. So it is 10 into 200 into 1000 is kilowatt second, right? Stored kinetic energy, it is equal to 2 into 10 to the power 6 kilowatt second, right? So second thing is your this thing, your what you call excess power input to the generator before the steam valve begins to close 20 megawatt. So this is that 20 megawatt data is given here, right? Therefore excess energy input to the rotating parts in 0.22 seconds will be 20 into 1000, so converted to kilowatt, into 0.22, so 4400 kilowatt second, right? Therefore stored kinetic energy is proportional to the square of frequency. Therefore frequency at the end of 0.22 second will be 60 into 2 into 10 to the power 6, 2 into 10 to the power 6 plus 4400 divided by 2 into 10 to the power 6 to the power half, right? Because it is square frequency at the end, square of the your what you call kinetic energy is proportional to the square of the frequency. So frequency at the end of this one, it will be this 60 into divided 60 is the frequency, right? So it is coming actually 60.066 hertz, right? So this is your idea, right? So this one, it is actually, you take for your, there should not be confusion, you take 200 megawatt generator, right? So such that this 200 in 1000 kilowatt, right, and H is given 10 second, H is 10 second, so it is PR into H, so rated capacity, actually it is rated capacity, so right. So this is 200 megawatt, not MVA, so it is 10 into 200 in 1000 kilowatt second. So this is a simple thing, I mean, as far as this what you call this problem is concerned. So frequency is increased to 0.066 hertz, right? So slightly above your nominal frequency. So more problems we will see. Let me finish this chapter. After that 3-4 problems I will take for you, right? So next one is the LFC of two area interconnected power system, right? Suppose you have a two area interconnected power system. So in this case, just I told you, suppose this is area 1, this is area 2, and what is control area also explained. This is a tie line. Tie line means nothing but a, you are to call 3-phase tie line, and this is a real power flowing P tie 1 2. Our interest about real power, we assume later we will see that this tie line resistance is less, I mean negligible compared to the reactance. So resistance part we will neglect, right? So rated area capacity of this one real power in terms of real power PR1, and area rated capacity of this one is PR2, right? And these two power system actually are interconnected. We call area 1 and area 2. So it is LFC of two area interconnected power system, right? So figure 17, this is figure 17. It shows a two area power system interconnected by tie line. Assume tie line resistance is negligible. We are not considering the tie line resistance, right? So this one, this line, this is a schematic diagram. right. This one we can write in little bit better way, right. Suppose PR1 is rated capacity of area 1 and PR2 rated capacity of area 2. Now this is two this side two bus bars are there, right. This is 1, this is 2, this tie line, current flowing from 1 to 2, say for example, say current is flowing from 1 to 2, it may be 2 to 1 also, no problem, right. But just we have taken here I12, this is the current. A resistance of this tie line, it is tie line means we are assuming it is a balanced thing, and it is a 3-phase transmission line, and you know for transmission line resistance is much smaller than the reactance, so R is neglected. But if you consider R also, model can be developed. Let me tell you, if you consider R also, so in that case whatever model will show you, it will be slightly different, but we will not consider that in this course. And another thing is that as soon as you consider the R, actually you will find response is slightly better, right, and in terms of your what you call settling time, because as soon as you consider R, resistance is line, and you know resistance actually adds damping. So anyway, we will not consider the resistance R. So in this case, suppose here load may be there. I have not shown here, but here load is PL1, here load is PL2, right. Anyway, this bus bar voltage is magnitude V1, initial angle was delta 1 0, and it is bus bar voltage magnitude V2, angle is delta 2 0, right. So and this power coming into this point, it is initially P tie 1 to 0 plus J Q tie 1 to 0, right. That is that scheduled power, that is initially, right. This is real power flowing from 1 to 2, and this is the reactive power in this direction, say 1 to 2. If it is not, it will be reversed, and resistance is neglected. So from your figure, this is your marked as figure 17a, right. Therefore, you know that from load flow studies, we know in general P minus JQ is equal to V conjugate I. So same equation we will write here. P tie to it is a superscript 0 means that in nominal value or schedule value, right, minus JQ tie 1 to 0 is equal to V1 conjugate I12, because this is the current flowing to this is I12, and this is the voltage your V1 actually in general phasor quantity. So magnitude is V1, and angle delta 1 0. We are writing P tie 1 to superscript 0 minus JQ tie 1 to 0 is equal to V1 conjugate I12. This is equation A. I have given this equation A, right. Now I12, the current flowing from this end to this end is equal to V1 minus V2 upon JX12. R is neglected, R12 is neglected. That means I12 is equal to V1 minus V2 upon JX12. So V1 is magnitude V1 angle delta 1 0 minus magnitude V2 angle delta 2 0 divided by JX12. This is equation B. From equation A and B we get. So equation A and B, what we will get? That P tie 12 minus J Q tie 12 0 0 are there superscript is equal to V1 conjugate into I12. This I12 here you substitute. This I12 value, this one you substitute. We are doing it and multiply. If you multiply, you will get P tie 1 to 0 minus J Q tie 1 to 0 is equal to magnitude. This one you substituted. So it is V1 conjugate. So it is magnitude V1 angle minus delta 1 0. So magnitude V1 angle delta 1 0 minus magnitude V2 angle delta 2 0 divided by JX2. Then you multiply. If you multiply, it will become magnitude V1 square. This delta 1 0 minus delta 1 0, it will become angle 0. So anyway, it is V1 square minus magnitude V1 V2 angle delta 2 0 minus delta 1 0 upon JX2, right. Then you have to do, you numerator and denominator you have to multiply by J, and then you separate real and imaginary part. So what you will do is that this one P tie 1 to 0 minus J Q tie is equal to V1 square minus magnitude V1 magnitude V2. Then this one you make it cos your angle theta is equal to cos theta plus J sin theta. So same way you make it here, right, minus magnitude V1 magnitude V2 cosine delta 2 minus delta 1 0, then minus J magnitude V1 magnitude V2 sin delta 2 0 minus delta 1 0, right. Or you multiply numerator and denominator by J. So P tie 1 to 0 minus J Q tie 1 to 0. Multiply numerator denominator, so J square, so it is minus, and here J is here. Rest of the thing in the bracket is the same thing here, Now this equation you multiply by J, then it will be like this: P tie 1 to 0 minus J Q tie 1 to 0 is equal to magnitude V1 upon magnitude V1 into magnitude V2 upon x12 sin delta 1 0 minus delta 2 0, right, minus J V1 square in bracket minus magnitude V1 minus magnitude cos delta 2 1 delta 2 0 minus delta 1 0 upon x12. So this one, as soon as you multiply by this equation by j, right, as soon as you multiply this equation by j, so it will become your what you call that your j is this v1 v2 sin delta 2 minus delta 1 minus x2, right. Now if you just numerator and denominator by your what you call minus numerator by minus 1, say, then in that case this will minus, but then instead of delta 2 minus delta 2 0 minus delta 1 0, we have taken that minus sign delta 1 0 minus delta 2 0, so ultimately it will become plus. That's why this is plus, right. And this, but that means our thing is not Q flow, our unit is only real power flow. So p tie 1 to 0 actually v1 v2 upon x12 sin delta 1 0 minus delta 1 0. This is equation C and this is equation D, right. Now this is that nominal power flow, that means p tie 1 to 0, this p tie 1 to 0 which is flowing, it is magnitude v1 magnitude v2 upon x12 sin of delta 1 0 minus delta 2 0, right. This is the power. Q we are not interested, our interest is only the real power, right. And let me tell you one thing, as the line resistance is neglected, that means whatever power is here p tie 1 2, so assuming that power is flowing in this direction, whatever p tie 1 2 is here, it will be same as here, because assuming line is lossless. If line is lossy, if line is a lossy line, I mean if you consider R, then whatever power will be here, it will not be the same power here, because that loss will be there. According to the direction of the power flow, that this loss has to be added, or your what you call subtracted from this value, from p tie 1 2. But in this case, resistance R is neglected for this line, therefore whatever power will be there p tie 1 to 0, it will be the same is here, right. I think it is understandable to you. So in this case, your p tie 1 to 0 is equal to this one. So next what we will do, suppose there is some disturbance in the load, some load disturbance is there, because load is here, I have not shown in the diagram, but load is here. For example, I am making it here. Suppose that load is here, load is here. So in that case, your what you call this side PL1 and this side PL2. So suppose there is some disturbance in the load, it may be in either of the areas. If the load disturbance is there, then what will happen? Then there will be change in the tie line power flow, there will be a change in the voltage angle also, but it is a real power change. We are assuming the load real power change, and earlier we told if real power changes, then frequency, hence the voltage angle may change, right, will change. But question is that voltage magnitude will not change, it will remain as it is. So based on this our this philosophy, right, what we can do is, now suppose if there is a load disturbance in either of the areas or in both the areas, I mean disturbance may be here or both the areas simultaneously, it can happen, right. So in that case, the angles delta 1 superscript is 0 and delta 2 0 will change, because real power changes. We are assuming load disturbance means we are assuming only real power, not reactive power in this case. Suppose real power changes, right. In reality both can change, but we are assuming small perturbation, only real power change. In that case, the delta 1 0 and delta will also change. Also for tie line power flow, I told you this one, earlier it was scheduled power flow p tie 1 to 0, now we will deviate from its actual value, because earlier some load was here, some power was flowing to the tie line. But as soon as load disturbance will happen, this tie line power flow also will change, along with that delta 2 0, delta 1 0 will change, because delta 1 0 delta to the frequency. This earlier your what you call, I told you several times, right. So delta 1 0 and delta 2 0, also later we will see how it can be related to the frequency, later we will see, right. So this will change. If it is so, change means small changes. If it is so, that means now the new values are delta 1, delta 2 and say p tie 1 2. These are new values. That means from this one, from equation D, that is p tie 1 2, v1 magnitude x12 sine of delta 1 minus delta 2. Earlier we are writing this one, that whatever we got, that p120, p tie 1 to 0 rather, is equal to magnitude v1 upon x12 sine delta 1 0 minus delta 2 0. But because of these load changes, now the new value has become that p tie 1 2 is equal to magnitude v1 by x12, because v1 v2 will be unaffected, sine delta 1 minus delta 2. This is equation E, right, because this is new value delta 1, delta 2 and p tie 1 2 because of your what you call load changes. Therefore, now delta 1 actually is equal to delta 1 0 plus delta 1. Initially it was delta 1 0. Now because of the delta 1 change, this is delta 1. Similarly, delta 2 initially it was delta 2 0, but because of this delta 2 change, delta 2 is equal to delta 0 plus delta 2. Right. Initially that it was p tie 1 to 0. Now because of this load disturbance has happened, so p tie 1 2 is equal to actually p tie 1 to 0 because this change delta p tie 1 2. All these things, rather than taking direct perturbation for your understanding what I have done, I made it detailed such that you will understand. All these things you put it here, put in this equation. That means delta 1 you substitute delta 1 0 plus delta 2 you substitute delta 2 0 plus delta, and p tie 1 2 is equal to p tie 1 to 0 plus delta. You put it here. Then we can write p tie 1 to 0 plus delta p tie 2 is equal to V1 magnitude V1 V2 upon x12 sine of delta 1 0 plus delta 1 minus delta 2 0 minus delta 2. Or you can write left hand side will remain same, magnitude V1 V2 upon x12 sine delta 1 0 minus delta 2 0 plus delta 1 minus delta 2. Right. Or you can write p tie 1 to 0 plus delta p tie 1 2 is equal to magnitude V1 magnitude V2 upon x12. Then it is your sine A plus B formula. So sine A cos B plus cos A sine B. This way you write. Right. So it is sine delta 1 0 minus delta 2 0 into cos delta 1 minus delta 2 plus cos delta 1 0 minus delta 2 0 into sine delta 1 minus delta 2. This is equation A. Now you have to make some simple assumptions. Assumptions are delta 1 minus delta 2 is very very small, right? So we can write then cosine of delta 1 minus delta 2 approximately equal to 1, and you know for small theta, if theta is very small, then sine theta is equal to theta. We can write, right? So here sine of delta 1 minus delta 2, you can write directly delta 1 minus delta 2. These two are assumptions, right? Because our objective is that we have to make it a linearized model, right? So if it is so, then here you put cos delta 1 minus delta 2 is 1, and sine delta 1 minus delta 2 is equal to delta 1 minus delta 2. You put it here, all this you put it here. If you do so, p tie 1 to 0 plus delta p tie 2 is equal to V1 V2 upon x12 sine of delta 1 0 minus delta 2 0 plus delta 1 minus delta 2 into cosine delta 1 0 minus delta 2 0. Or you can write p tie 1 to 0 plus delta p tie 1 2 is equal to magnitude V1 magnitude V2 upon x12 into this term sine delta 1 0 minus delta 2 0 plus your magnitude V1 magnitude V2 upon x12 into this term cos delta 1 0 minus delta 2 0 into delta 1 minus delta 2. Or p tie 1 to 0 plus delta p tie 1 2, this term earlier we have written, no, p tie 1 to 0 actually magnitude V1 magnitude V2 upon x12 sine delta 1 0 minus delta 2 0. This term is equal to p tie 1 to 0 plus this additional term has come magnitude V1 magnitude V2 cosine delta 1 0 minus delta 2 0 upon x12 into delta 1 minus delta 2. So p tie 2 0 both sides will be cancelled, and we will get a small perturbation expression of delta p tie 1 2 is equal to this one will be cancelled, right? That means delta p tie 1 2, right, is equal to V1 V2 cosine delta 1 0 minus delta 2 0 upon x12 into delta 1 minus delta 2, right? Next is both sides, because this is power flowing from 1 to 2, so both sides what you can do is, this is your rated capacity of area 1 PR1, so both sides that power is flowing from your this thing from 1 to 2, and rated capacity of this side is PR1, this is your PR1, so both sides you divide it by PR1. If you divide by PR1, delta p tie 2 upon PR1 is equal to V1 V2 cosine delta 1 0 minus delta 2 0 upon PR1 into x12 into delta 1 minus delta 2. Or this is converted to per unit, delta p tie 1 to per unit. This term we are defining as whole thing as T12 into delta, we will come to that, what is this, into delta 1 minus delta 2. This is equation 23, right? Thank you.